So my name is Szymon. I'm from Poland. I'm currently doing my PhD at Astrophysics Division at National Center for Nuclear Research. Originally, I graduated from computer science with specialization in data science. Then I worked some time in business, and now I have the pleasure to be working in Astroinformatics. So the work I did with one of my two supervisors, Maciej Bilicki, who's also working in Leiden Observatory, together with Aleksandra Solarz and Agnieszka Pollo. So this is a quick outline, and we are going to introduce the kit survey and the training and inference data sets. Then we are going to talk about model training. Then we'll move to creation of catalog and important thing of feature space limitation to match training and inference data sets. And then very important, this is actually where quasars are mostly taken into consideration, because this so far is just photometric classification with some metrics for quasars. But here we also use some external data sources, which is important in machine learning to have some evaluation methods which use data sources apart from those used during the training to really see how your model is doing. So for this we use second data release of GAIA to see whether our quasars have zero parallaxes and proper motions, because that's what's expected. We use some external quasar catalogs to see whether classifications of our methods and some other methods match with predictions. Some simple number counts and manual check of some of the objects. So data, this is kind of degree survey. Currently the fourth data release is incoming in several months, and it has 4 photometric filters, UG, R, and I, and there are about 50 million of objects. And the gray here is data that's not yet available. It's going to come with future data releases. So this is first step data cleaning, important in machine learning. Important thing here is that we start with 50 million objects. Then after data cleaning, we have only 9 million of objects. Something we want to test later on is trying to use bigger errors, use some missing values. Those are things we want to test. But right now we were focusing on creating first pipeline, which actually creates a pure catalog of quasars. And the last step is reduction of feature space to match the inference dataset. We end up with 3.4 million of objects. This is training dataset from cross-match with SDSS, cleaning based on that wording, and we have 50,000 of objects in training, from which 7,000 are quasars. So looks pretty good. Now model training. Sorry if I'm running quite quick through the slides, but there's a lot of things, so it's better, I guess, to say briefly about everything than not say about something. So our evaluation method is that we take 20% random sample of the training data set as a test set. Then from the remaining 80% we do 5-fold cross validation. Validation data set, from validation results we pick our model, and then all the results we will be showing are from the test sample. We use 3-class accuracy because we have galaxies, stars, and quasars, and we train 3-class model because this fits the model with the most information. But then we also focus on just binary classification, where we transfer the output to quasar versus rest problem by simply summing the probabilities of stars and galaxies into one class. And here we use accuracy, purity, completeness, F1, and ROC, AUC. Now for models, we tested several of the most commonly used models: gradient boosting from XGBoost library, random forest SVMs from scikit-learn, and also neural networks built with Keras and TensorFlow. And the changes in results were not so big, and this is probably due to the fact, and we also talk about the KNNs for photometric registries. What I believe is that the problems are too simple for those machine learning models, because if we are talking about 3 classes and 17 features, then XGBoost, usually people are using those for problems with hundreds of features or hundreds of classes. So for our problem, it's not easy problem to solve because we need more magnitudes, for instance. But as far as the models are concerned, it's not that hard problem. So we get the best results with XGB, but after several hours of tuning the parameters, and random forest provides almost the same results. So we usually run random forest, and then in the end we can spend some more hours to tune the XGB. But the random forest is our base model. Feature selection, what we did is we took everything from the kit survey, which are magnitudes, different kinds of magnitudes, colors, ratios, also not colors which are like G minus I, but also ratios which are G divided by I. The sextractor classifier, which tells you whether object is point-like or extended. fluxes, errors, and ellipticity. And then we create this ranking of feature importance. We take those features which provide the best results, and those are, it turns out to be 4 magnitudes, GAP magnitudes, colors, magnitude rates, and also the parameters which tells you whether object is point-like or not. This is a very important parameter because it allows you to easily get rid of all the galaxies from your sample, and then you are left with Kuzo versus star problem, and next features are responsible for this problem mostly. Okay, those are the results. So we have free-class accuracy very high, 97%, and the purity and completeness of our catalog is estimated at the training sample to be 91 and 87%. So far, very good results, right? But let's see on some of the errors. With UGR and I magnitudes, the colors for quasars and for quasars at redshift 2.7 look the same as for stars. So here we can see that we have some of the SDSS quasars. Those are SDSS quasars with different classification outcome. We have some of the quasars classified as stars here, and some of quasars, actually you can see the line here. There are galaxies here. Sorry, I didn't know it's not going to be visible. There are also some quasars classified as galaxies, but later on we checked those objects, and it actually turns out that half of them are actually galaxies, and SDSS was mistaken. And here you can see that from our predicted labels, what we predict that is quasar, we will have some contamination with stars. And also from the true quasars, we have some of them classified as stars and some of them classified as galaxies. So those are the groups here. So this allows us to see where the contamination will be coming from. And this is the t-SNP visualization which we used on the training data set. And this is very quite important. This is the same visualization, but with magnitude added as a color, so you can get nice interpretation of what's here. An important thing here is that the fact that some quasars are not distinguishable from stars is visible here. We have group of quasars here, and we have stars here, which are not distinguishable from quasars. But the important thing here is that once we train our model, then quasars here should have definitely lower probabilities than quasars over here, because they will have some stars in their neighborhood, and for random forest, some of the trees will be saying that those are actually stars. So what we say is that those elements, even though they are distinguishable, we can get rid of those quasars from our final catalog. And we'll be doing this, for instance, by using GAIA and the external evaluation methods. But this for now is to see how the training sample looks like and whether the problems are there or not. Because by simply looking at those numbers, it doesn't show us whether this problem is present or not. Here we can nicely see it. So we have a model. Now we move to creation of catalog. We need to make sure that the feature space is the same. What we do is we cut the R magnitude R value 22. This is an example of why such a cut might not work. I did some, created some data set. Those are two-dimensional data set, and you can see that with both of those features, there is some mismatch between the feature space. What we can do is we can cut these values at -1 and 1, -1 and 1. This is probably a very easy example. We are all know that this may work like this, but actually the distribution looks like this. I split this into completely not overlapping parts. So now if we do the cut, this is the cut, and we say that, oh, the training space and inference data feature space match, but actually not. They are completely not overlapping here. So it's very important to use high dimensionality visualizations. So here, the pink color is something we want to get rid of because those are elements from kits which are not in SDSS. And here we have some labels from SDSS. This classification will be okay, but this will not be okay. And the right is different colors. I'm not going to explain that, but again, the pink one is our R cut, cutting the R magnitude. And we can see, for instance, here that what we want to do is we want to have a line over here, because these are quasars. We are going to classify quasars here, and we want to get rid of this part and this part. And actually, this is what this cut is doing. All of those things are removed. Here we can see that maybe it could go a little bit deeper, so we can also estimate how good our cut is performing. Some better work could be done here, but for now it's not the biggest problem, and we leave it like this. So this is a result of prediction on the KISS dataset. From 3.4 million of objects, we find 192,000 of quasars. Okay, and now we want to see whether those quasars are really quasars. And for those, we are using some external datasets which were not used during training. First one is GAIA second data release. It's not a lot of time to talk exactly how it works, but what we do is we take our quasar candidates and we want to make sure that the distribution of parallaxes and proper motions is of zero mean, because there is some noise, so you cannot explain that those are zero values, but it is zero mean. And once this is taken from the GAIA paper, Astrometric solution for GAIA DR2, this is cleaning because there are some values, very high values for proper motions, parallaxes, which are not correlated with the uncertainties, and it's not really well stated in GAIA as far as I know. If someone knows how to do it better, then I'm glad to discuss it. What the proper cleaning method is. So we do some cleaning, we reduce the number of quasars from 38,000 in the cross-section of our catalog with GAIA to 23,000, and now we see that by normalizing the parallaxes and the proper motions by the error, what we expect is a distribution of 0 mean and 1 sigma, and we get this for parallax values almost. For the inclination proper motion, there is some offset, and this is our cleaning approach. Once we limit our quasar catalog to objects with score with probability higher than 0.7, for instance, we get a much cleaner sample, which is much closer to zero. Those are proper motions for those are means of proper motions, declination and right extension proper motion. So this is perfect. We say that here should be also fine, because we do have some contamination, and we cannot get rid of this at like in 100%. So by doing this cut, we are left with 107,000 quasars, which should be rather clean. So this is very nice way of using GAIA, and this is a really strong tool. We also use some external quasar catalogs, and here we simply see that from those quasars, how much our model agrees with those predictions. And what we see is that with deeper catalogs, this is photometric catalog, those are, this is spectroscopic catalog, those are photometric ones. Deeper catalog will have smaller overlap with our classification. So there is for sure this effect that with deeper object, the classification have added those models or our model or all of the models is worse. And this is a way of saying how much worse can it be. But generally the numbers are rather good. This simple number count, which shows you that training quasars are not sufficient here. Our quasars clean sample rise in a regular way, but this is obviously very simple analysis, but shows that it behaves the way it should. And we also did some manual check on the SDSS quasars, which our model classified as galaxies, and we take 50 randomly chosen ones, and it turns out that 50% of them are actually AGNs, but 50%, but the other part are other starbursts or just galaxies. So actually, our model can fix some of the misclassified SDSS objects, and from the 17 objects, but this is just from the test sample, 20% random sample, which SDS quasars, which our model says with 100% probability that those are galaxies. We have 14 which are actually galaxies and not AGNs. Okay, this I will skip. And this last slide, what is the future plan? We want to add infrared from Viking survey, this survey which overlaps in the sky with KITS, and this will greatly enhance the classification capabilities. We want to add set features into our model, which also should do better. And something which I'm mostly excited about is a model which does this neural network with some features, and classification and redshift estimation is being done by just one model. I've seen papers so far which, for instance, do classification either photometric redshift, but so far, I don't know, maybe you are aware of such models. I didn't see them which do both of those together, and this should enhance both of those tasks together, and they should do better. And redshifts here can be either just a redshift value or also can be another outputs here plotted with PDF's estimation. It can be more outputs added here. So yeah, thank you.